Yes. Well, so in our last lecture we were discussing the idea of angle between two curves over a surface. So throughout we have been assuming that a equation of the type r equal to r of u1 u2 represents a surface in R3. u1 u2 are called the parameters. So what we were doing, we were considering curves on these surfaces. So if C1 is one curve over it given by u1 equal to u1t and u2 equal to u2t, that is u1 and u2 becomes function of a single parameter t. u1 u2 are variables varying over the surface, then this will give you some curve over it. So in short, you can write down ui equal to uit. So suppose this is a curve on the surface sigma, and suppose there is another curve C2, which you can say u1 equal to u1 tau, u2 equal to u2 tau, tau is some other parameter, or in short you can also write ui equal to ui tau. So this is another curve, and suppose they intersect each other at certain point on the surface. So let C1 and C2 be two curves on sigma intersecting at certain point, intersecting at a point P, and this point P it is some point on the surface. So what we do, we draw tangent at P to C1, this is C1, this is C2, and also tangent to the curve C2 at P. So these are the two tangent vectors. The idea is that you just compute the angle between the tangent between the two tangent on C1 and C2. So the angle between C1 and C2 and C2 is defined as the angle between the tangents to C1 C2 at P. This is how we define the angle between two curves. So the tangent to the first curve C1 is given by tangent to C1 and C2 are what they are. The tangent to the C1 is, I will call as dr. So this is Ri into dui, okay. And the tangent to C2 I will denote by the symbol delta r. This is equal to some r j delta u j, where del is the differential operator along C2, d is the differential operator on C1. So these are the tangents on C1 and C2. Now the angle theta, if theta is the angle between C1 and C2, then cos theta must be equal to dr dot delta r upon modulus of dr into modulus of delta r. This is the usual formula of cosine theta in R3. So these tangent vectors are vectors of R3 also. So we can make use of this formula. Dr is Ri dui, del r is r j delta u j, mod dr and mod del r I will keep as it is. So, the numerator becomes g I j into du I delta u j upon mod dr mod delta r. This is cosine theta. This formula we discussed in our last lecture. I will call it number 1. Now, one can compute sin theta also. Sin theta similarly, I can work out sin theta, that must be equal to modulus of dr cross delta r. If you recall the formula for cross product, you will notice that sin theta must be this, and let us simplify it. So, this is r I du I cross r j delta u j, take the cross product and you can divide by modulus also, mod dr mod delta r, here also mod dr delta r are there. So, this will become, after simplification, it will become r 1 cross r 2 into du 1 delta u 2 and minus du 2 delta u 1. You can check it up when you will compute the cross product. Keep in mind the signature, it will be this much upon modulus of dr into delta r. Whether this much is visible in the book? Okay. So, sin theta is this much, you may call it number 2. All right. R 1 cross R 2 you can call as under root g. So, I can replace R 1 cross R 2 by under root g. In the next step, you may write down equal to under root g into du 1 du 2. Okay. So, let me rewrite down. If it is not visible, this becomes under root g du 1 delta u 2 minus du 2 delta u 1 upon mod dr mod delta r. Okay. This is number 2. Number 2. Let's so these two expressions are there. Now, I come. Yes, mod g, whether this, okay, and this, yes, okay. All right. Now, I computed this formula in order to discuss one exercise with you. The exercise is for the curves. Now, I can discuss this example. For the curves, given by this differential equation, given by the differential equation a du square plus 2b du 1 square, 2b du 1 du 2 plus g no c into du 2 square equal to 0. So, curves are a family of curve is represented by this differential equation over a surface whose parameters are u 1 and u 2. For these curves, what we have to do? We have to show that for the curve this, show that tan theta equal to 2 times under root g into under root b square minus ac upon EC minus 2 BF plus GA. All the symbols I explained to you in my earlier lecture, that E is G11, F is G12 and capital G is G22. A, B, C are given here as coefficients, so in this differential equation. Okay. So, let us try to resolve this problem. Oh, using the right decision. All right. So, tan theta must be equal to cos theta sin theta upon cos theta. Both the expressions are available to me. Okay, let me call this differential equation as number 3. I can rewrite number 3 as follows, rewriting as follows: a into du1 over du2 whole square, I am dividing throughout by du2 square, plus 2b du1 over du2 plus c equal to 0. Sorry, the form of the differential equation that we have, which represents family of curves. Now, if I look at this equation as a quadratic equation, then this quadratic equation will have two roots, du1 upon du2 and the other you may call as delta u1 upon delta u2. So, they will correspond to the slope of the two families of curves. Okay. So, whenever such a differential equation is written, you can understand they will represent two families of curve and the roots of this equation will correspond to the slope of the two families. Okay. So, the roots say du1 over du2 and delta u1 over delta u2 will correspond to of the above quadratic equation, will correspond to the slopes of the two families of curves. Okay. Now, we can see what are the sum of the roots and the product of the root. So, sum of the roots which is du1 over du2 plus delta u1 over delta u2. This you can check from here is minus 2b over a, and the product of the roots will be du1 upon du2 into delta u1 over delta u2, that is equal to c upon a. Okay. Now, I can rewrite this equation 2 as the difference of the root. Okay. So, if you wish, you can write down sin theta again. Okay, here itself. I can write down sin theta again like this, equal to under root g. I am dividing by du2 delta u2. So, when you divide the whole thing by du2, so this will become du1 over du2 minus delta u1 upon delta u2. So, when you have divided, you must multiply also. So, du2 into du2 into delta u1, no, delta u2, okay, upon mod dr mod dr delta. So, sin theta can also be written like this. Okay. So, now the difference I can compute from these two relations. So, du1 upon du2 minus delta u1 upon delta u2 will be this square under root, means 4b square upon a square minus 4 c upon a. So, this will become 1 upon a, 2 upon a into under root b square minus ac. This is the difference. Okay. Now, tan theta I can write down as sin theta upon cos theta. So, I have to remove this part. So, hence tan theta is equal to sin theta is here, which I have rewritten like this, under root g and 2 times upon a into under root b square minus ac. And then you have that term also, and mod dr, okay, du2 delta u2 upon mod dr mod delta r, okay, and cosine theta is here, okay, it is okay. Let me expand it, cosine theta. So, in the expanded form, it will become g11 into du1 delta u1 plus g12 du1 delta u2 plus du2 delta u1 plus g22, and then you have 1 upon modulus of dr into modulus of delta r, that I will cancel out from here. And here also, okay, yes, du2 delta u2 also. Now, in the denominator also you can divide throughout by du2 delta u2. So, when you will divide the denominator by du2 into delta u2, what will happen is under root b square minus ac, and I am dividing throughout by du2 delta u2. So, I need to multiply also, and when you will multiply, this term will also get cancelled, and you will be having only g11 into du1 upon du2 square plus I am multiplying and dividing by du2 square Okay. Okay. No, not this. Yes, into del u1 upon del u2. You are right. And plus G12 du1 over du2 plus delta u1 over del u2 plus G22. Okay. du2 into delta u2 has been cancelled out. I have cancelled over there. Okay. All right. So, now we can substitute the value over here also for the sum and product. So, you have in the numerator under root g upon a twice b square minus ac, and in the denominator G11 you may call as E, product of the root is C upon A, you have just seen, plus G12 you are calling F, sum is minus 2B over A and plus G. G22 is capital G. So, you take 1 upon A common from here also, and then you cancel it with this 1 upon A. So, you will be getting 2 under root G into B square minus AC upon EC minus 2BF plus GA, and that is what you wanted to show. So, you can compute now tan theta, cot theta and sec theta as well. So, this is how we solve problems on angles. Okay. Some of the problems are there in the lecture notes also. So, student may try by themselves. So, now we move on to another topic, that is the area of a surface. How can we make use of all these things in computing the area of a surface, of a compact surface, area on a surface. If a surface is non-compact, then you cannot compute its entire area, but you can always decompose into several parts, several regions whose areas can always be computed. So, let us consider a surface represented by a parametric equation R of u1 u2. So, the idea is what you do is you just draw parametric curves over the surface. Suppose these are u1 curves, this is the family of u1 curves, and then you draw u2 curves. So, these parametric curve will divide the whole surface into small patches. You pick one patch, for example, I pick the patch, call it P, Q, R and S. So, what we will be doing, we will compute the area of a patch PQRS. So, let PQRS be a patch on the surface sigma. This is the surface sigma, and this patch is bounded by parametric curves. So, PQRS be a patch on the surface bounded by parametric curves. And then you draw tangents at the point P to these parametric curves. Suppose at the point P I draw tangent to this u1 curve, this is the tangent to the u1 curve, and at the same point you draw tangent to u2 curve. Suppose this is the tangent to u2 curve. Okay. let me consider the coordinates of the point. So, suppose P has coordinates u1, u2. These are parametric coordinates of the point P, and Q also lies on the same curve, let us say u1 curve, then its coordinates will be some u1 plus du1 and u2. This will be the coordinate of Q. Coordinate of R will be u1 plus some du1 and u2 plus du2, and coordinate of S must be u1 comma u2 plus du2. Okay. I can draw the entire patch PQRS over here. So, this is the patch PQRS, P, Q, R and S, and then I have drawn tangents at the point P. So, these tangents, what I will do, I will complete the parallelogram. So, tangent is up to here, say this is Q dash and this is S dash. So, I will complete the parallelogram. Okay. Q dash and this is R dash. Okay. So, complete the parallelogram P Q dash R dash S dash. So, let P Q dash and P S dash be tangents, tangent vector rather, tangents to the parametric curves. At P. Next, you complete the parallelogram, P Q dash R dash S dash, as I have shown you in the figure. Now, when the parametric curves are chosen very close to each other, the area of the parallelogram P Q dash R dash S dash will be same as the area of the patch P Q R S. So, in the limiting case, these two areas must be same. Okay. So, when the parametric curves are chosen close to each other, when the parametric curves are very close to each other, the area of the parallelogram P Q dash R dash S dash is equal to, approximately equal to, the area of the patch P Q R S. So, area of the patch. So, this region or this patch is in fact the image of a small rectangle in the plane. Okay. So, the image of this small rectangle is in fact this patch P Q R S. So, this rectangle here you have u1 varying here, u2 varying over here. Okay. Let me call this area of this rectangle as omega. Okay. So, area of the parallelogram P Q dash R dash S dash is equal to it will be, what are the tangents? Tangent at P. Let me write down somewhere the tangent at P. P q dash is the tangent at P to the u1 curve. If you look at this, it will be r1 du1. Am I right? It is on u1 curve. So, u2 is 0 constant. So, du2 will be 0, and ps dash, the adjacent side of the parallelogram, will be equal to r2 du2. So, these are the tangents, these are the adjacent sides of the parallelogram p q dash r dash. So, the area of the parallelogram must be equal to, we know that. So, we know that. Okay. Area of the parallelogram is equal to the cross product p q dash p s dash modulus area. So, p q dash is r1 into du1 cross r2 into du2, and that will be equal to r1 cross r2 into du1 du2. Okay. So, this is area of the rectangle or parallelogram. Okay. So, now the area of the entire surface can be computed by integrating this area over the surface. So, the area of a region, because surface may not be compact. So, area of a region on the surface, area of a region on the surface is equal to integral, double integral, because you have modulus of r1 cross r2 into du1. Okay. And this will be, this r1 cross r2 is under root g, it is invariant of the surface. So, this will come out into integral over omega du1 du2. So, this is how we compute the area of a region in a surface. If the surface is compact, you can compute the area of the entire surface. So, this is the formula for the area, which can be used in some for known surfaces. So, I can leave one exercise over here. A sphere is a compact surface. So, we can compute its area. We know what are the parameter u1, u2, where they are varying, in which interval they are varying. So, that give you the idea of the upper and lower limit of this double integral. Okay. So, find the area. Surface area. Area means surface area, or nothing else can be there. But you, yes, we already know what the area of a sphere is, but you try to make use of this formula. Yes, yes. Find the area of the surface area of the sphere. S2. Okay. S2 means set of all x, y, z in R3 such that x square plus y square plus z square equal to a square. Okay. So, you can convert the equation into parametric form, and then you can compute the area by using this formula. So, this is the last thing of the unit. No, there are few more things, some coordinate transformation. So, the next I will be discussing some coordinate transformation after a break of 5 minutes. Okay.